Hi everyone. So today I'm going to be demonstrating how to construct your own musical step sequencer with the software Max 7. If you remember, a step sequencer is a feature of a synthesizer that creates patterns of notes and rhythms, kind of like this. You get the idea. Along with making an interactive step sequencer that can be played in real time, like you just saw me doing, you will learn how to do some additive synthesis, that is, combining simple waveforms together to make a more complex sound. You can think of this as making your own sonic recipe. As Max 7 is software, what we're going to do is actually an example of computer music. Max, originally known as Maximus P, was created at IRCAM in Paris, France by Miller Puckett and collaborators in the 1980s. At the time, live processing of audio with a computer was difficult and practically unheard of. Miller and his collaborators got the idea for Max by studying analog modular synthesizers. What if you could create little pieces of code representing various audio processes, such as oscillators, filters, delays, and much, much more, and hook them together visually with virtual cables? This is how Max became a visual programming language, designed to somewhat resemble working with an analog synthesizer. Unlike an analog synth, Max can also be used to work with audio samples, like recorded audio samples. It can take in data from sensors, such as EEGs, which are used to measure brainwaves, and it can process live acoustic signals in real time. For example, the music played by maybe a flutist or someone playing the guitar. Today's goals are the following. 1. Learn key commands, patching syntax, and workflow. 2. Print to the Max console. 3. Create a basic waveform and send out of computer speakers. 4. Build an interactive step sequencer with time controls. And 5. Learn how to sculpt waveforms through additive synthesis. But first off, let's get some Max basics down. So let's create a new patch. To create a new patch, go up to File, choose New Patcher. You see here that you've got a blank window. This is what a new patch looks like. Okay, so what we're going to do is we're going to populate this with pieces of visual code. There are 3 categories here that we're going to focus on. The first is objects, the second is messages, and the third is comments. Again, these are little visual pieces of code that accomplish different things. Objects are going to do all the heavy lifting here. These are the most interactive bits of code, and they look, for example, like this. See, you can play with them in real time. Okay. Messages are things that talk to objects, and for the most part, they aren't interactive. They look like this. Okay. Finally, comments are things you write to yourself in your patch for labeling or documentation purposes. They look like this.
Like mine would have been like, yeah, it's going to be something.
Well, it was in the form of alias. I think I cashed it all.
Okay. You can create objects, messages, or comments by using key commands. So, the key command for object is going to be N. The key command for message is going to be N.
What? Oh, that's weird.
And the key command for comment is going to be C. So what that means is that if you just press N on your keyboard, an object, a new object will appear, and it will be ready for you to type into. So I'm going to just make a number object again. Okay. Cool. I'm going to make a message. I'll just give it a 1, and I'll make a comment. So this is a good time to practice doing this a little bit in your Patcher. Okay, so Max has 2 modes. It has 2 modes, and they're called locked and unlocked. You can think of locked mode as play mode and unlocked mode as edit mode. When the patch is unlocked, like you see it here, you can create objects and hook them together. So I could hook number box to another number box, for example, like so, and then they would mirror each other. You never really want to do that in a real patch, but just for demonstration. Okay. When the patch is locked, that's when you can play with things. So again, locked, unlocked, locked. Okay, my patch is unlocked now, so I'm going to delete my number objects, my message, and my comments. I'm going to leave these here because they're handy. Okay. So now we're ready to start hooking some objects together. So I'm going to show you guys, before we get into making a sequencer, how to print to the Max console. Okay, what is the Max console? The Max console is a little window that you can access by going over here to the right side of your patcher, and inside of it you can basically get a stream of information that's coming through the software. So what the print object does, so again, if you press N, you'll get the object. You can type print to create your object. What the print object does is it takes whatever you send to it and it makes it show up in the Max console. So to demonstrate what a few really handy objects do, we're going to use the print object. So 4 objects I want to show today are an object called bang, an object called toggle, an object called number, and an object called floatum, or floating point decimals. Number, by the way, is integers. Okay, so to create a bang, I'm going to use the key command B. Oops. Okay. And you see it looks like a little button. So you notice on either side of the bang, on the left-hand side, there are what are called inlets and outlets. So you can think of red as being the inlet and yellow is the outlet. Information flow only goes one way in Max. From inlet to outlet, information always comes in the inlet and goes out the outlet. You can think of your phone charger. Energy flows from the power outlet to your phone, not the other way around. So if I hook this up to print, I'm sending whatever is coming from this object to print, and print does not talk back to this. So I'm going to hook my bang object up to print. I'm going to lock my patch, and then that means I can interact. So I'm going to click, and basically what I'm getting is that print is just printing a series of bangs. Okay, next object. I'm just going to leave that hooked up. So yeah, a bang is useful if you want to trigger a process, basically. If you want to say go to anything, you can just hook up this button, bang, and press it, and whatever you hooked it up to will just go. Okay, so next is our toggle. To create a toggle, you're going to use the key command T. So you can think of a toggle as a switch. If it's clicked, it goes on and it sends a 1, and if it's clicked again, it goes off and it sends a 0. So you can see it printing there in the Max console. You can see what it's doing. It sends a series of 1 and 0s alternating every time I click on it. So this is good if you have a process that you want to be able to turn on and off at will. Okay, next object, number. So the key command for number is actually I for integer. If I press I get my number, and if I hook it up to the print object, lock my patch, you can see in the print console that I am printing a stream of whatever numbers are running through here. By the way that you do that is you click on the little arrow inside the number box and scroll your mouse up and down. That's how you get interactive numbers. Okay, the last one is phlonem, so that's for decimals, and the key command for that is F. So I gotta make sure my patch is unlocked. I'm gonna press F. There's my floating point decimal, and I can see the decimal there. Hook it up to print, lock my patch, and I can play with numbers. If I want to actually scroll up and down in decimals, I can move my mouse over to this portion of the object and scroll up and down to get a finer grain of decimal numbers. Okay, so now that goals 1 and 2 have been covered, you can see that I deleted all that stuff and just left this handy list of key commands on the side here. Let's make some sound. So next up is 3, which is to create a basic waveform and send it out of the computer speakers. Okay, so you can see I've already created this object here. This is called an easy DAC. If you remember what a DAC is, it's a digital analog converter. Basically meaning that we're converting whatever numbers we're getting out of our computer into voltages, which will be converted into sound that comes out of our speakers. So to make an easy DAC, make sure that your patch is unlocked. Hit N to make an object. Type EZDAC tilde, not to be confused with easy ADAC. So yeah, make sure that the hint says audio output and on-off button. Hit enter, and you'll have this nice little GUI object. I already have one, so I'm going to delete that. Now, it's nice that we have a speaker, but nothing's coming out of it. So let's make some waveform. Let's send some signal out of the speakers. So to do that, I have a few options. So very similar to an analog modular synthesizer, Max has some basic oscillators. They're digital, but they kind of mimic the kinds of oscillations that analog synths could make. So if we think about some really basic waveforms, sine waves, triangle waves, sawtooth waves, those are all available. So making sure that my patch is unlocked, I'm going to hit N, and I'm going to make a sine wave. In Max, the object for sine wave is actually cycle, tilde. I'm going to hit Enter, and I've got a sine wave. So what is this tilde all about? Well, the tilde is used for objects that specifically deal with signals and sample rate rather than just numbers. So numbers, objects without tildes only send numbers, and objects with tildes send signals. Okay, so you'll notice here that if I type cycle tilde into my object and hit enter, it will ask me for these things called arguments. So you can think of arguments as some beginning parameters that an object needs in order to function. Not all arguments are necessary, but some arguments are, and they're kind of listed in order of importance. So we see that our top arguments here is frequency number. Basically, at what frequency do we want our sine wave to oscillate? It's going to be in hertz. Let's choose something nice and low, but not too low. So let's go for 300 hertz. That means 300 cycles per second. I'm going to hit enter, and I've got a sine wave oscillating at 300 hertz. It's not going anywhere yet though, so if we want to make it go somewhere, I'm going to have to hook it up to our DAC. And if you remember from the last section when we made stuff print, signal's always going to go from the outlet into the inlet of the thing you're sending it to, and it doesn't go the other way. So I want to send my signal out of the speakers. So I'm going to hook my cycle up to my DAC. My DAC is actually by default 2 channels, stereo, because nearly everything is stereo these days, and our computer speakers are stereo. And now you can hear that I have a sine wave buzzing along at 300 hertz. Okay. Wonderful. Now if I want to make a different waveform, I have a few options. I can do a triangle wave by typing tri tilde. Going to give that a frequency of 300 hertz as well. And I also have an option of a sawtooth wave. If I type saw tilde, hit space, let's give that a frequency of 300. And just to hear the difference in timbre, here's our sine wave. You can delete these patch cables by clicking on them or pressing shift-click to get both of them. Hit delete, and I can replace that with my triangle wave. And then if I want to hear what my sawtooth wave sounds like, I can do the same thing. So as you probably recall, sawtooth wave tends to have a much sharper, brighter sound than triangle wave or sine wave. That's because it has more harmonics, it has more high frequency content. Okay. So that actually completes step 3 of the demo, which is to create a basic waveform and send it out of the computer speakers. So if you've done that, congratulations. Now we're going to use these waveforms to be the drivers for our sound for our step sequencer. So whichever one you like, choose it and delete the others. I am going to choose the triangle wave because I like the way that one sounds the best. And I'm going to leave it hooked up to my speakers at this point. Alrighty. Okay. So say I want to be able to control the frequency of my triangle wave, so it's not just always buzzing along at 300 hertz. Well, I can actually do that in real time. So one thing that's nice about objects and Macs is that if you mouse over the inlets like so, they give you hints about what can go into that inlet. So you'll see on this left-hand inlet that triangle tilde it's asking for a frequency. This means that we can change it in real time. So I'm going to make an integer. I'm going to hook that up to my triangle wave. And I'm just going to scroll through frequencies by making sure my patch is locked, grabbing the arrow, and scrolling up and down. Okay, so actually I can sort of start to play with sound in real time and perform it a little. But this isn't a very elegant way of controlling an oscillator, and it's not anything close to a step sequencer. So I'm going to delete that for now. What I want to do instead is I kind of want to give this object, this triangle wave object, a series of frequencies that will tell it to jump around or step around on different pitches in a pattern. And so now that we're done with step 3, we can start to build our interactive step sequencer. So a really handy object that I like to use for controlling a step sequencer is this thing called a table. So to make the table, which is an object, you press N, type table, hit space. You'll see that its only argument is that it needs a name. So you can name it whatever you want. I'm going to name my table triangle, because I'm using a triangle wave. Hit space. And here we have the opportunity to specify the number of steps that we want our table to be. If you remember talking about analog modular synthesizers, it was very common for patterns to happen in 4, 8, or 12 steps. So let's specify that we want 12 steps. To do that, I'm going to use this thing called attributes, which is another way of specifying beginning sort of default parameters for certain kinds of objects. So I'm going to use the size attribute. If I hit space, I get to specify the number of values I want in my table. So I'm going to use 8. I think 8 is a nice number. Hit enter, and my table is created. Okay, now if I lock my patch and I double click on the table, I get this nice little window here. And you'll see that I can actually mouse around inside of it and draw in data points. You'll also see that because of my request that it's 8 steps, it has 8 values on the x-axis. A really important thing to note is that it actually starts at 0. So that means that even though it has 8 steps, the values are indexed from 0 to 7. Okay, so I'm just going to draw on a nice little curve of values here. Yeah, let's make it go like down and then up. Okay, Gonna click out of that. Okay. So what this is going to be used for eventually is it's going to be used to control this, okay? So there's nothing particularly special about a table. It's just a thing that stores numbers. You can also think about it as indexing values. So if you think of x being an index number, you can think of the y-axis as being the values you are getting out of it. To show you what I mean, I'll demonstrate that if you give table an x value, it will actually spit out the corresponding y value. Let's test that. So I'm going to hit I to make myself a number, an integer. I'm going to hook that up to table. On the other end, I'm going to make another integer, and I'm going to say, table, send whatever you're doing out to this integer. Now, if I remember, since I have 8 steps here, if I give table a value between 0 and 7, it should spit out the corresponding y value. So to do that, I'm going to make sure my patch is locked. I'm going to hit, let's just try 1. I'm going to hit enter, and voila, table has produced the corresponding y value. And if I double click on it and go inside this window, I can go to 1, and I can actually mouse over it and see that, yes, x is 1 and y is 52. Okay. So I can, play around with it and see what y values it's spitting out. But I can guarantee you that it is consistent. Okay. So for our purposes, we don't actually need these, but what we want to do is we want to take whatever y value is coming out, and we want to use that to control the frequency of this triangle oscillator. So let's just open this up again and take a look at what our y values are. So we've got 54, 52, 47, 42. Those are pretty low. Like if you think about 42 hertz being translated, or 42 being translated into 42 hertz, that's an incredibly low frequency. And because the human hearing range is so broad, it wouldn't really make a lot of sense to convert these values directly into frequency with no transformation. So that's where this really handy little object called MIDI to frequency comes in. The spelling of that is M2F, and you'll see the hint here says convert a MIDI note number to frequency. Hit enter and it's made. Basically what this object does is it takes whatever's coming in and it treats it like it's notes on a piano. So, pitches in the Western classical music scale. And actually does a math and translates it into frequency. So now, whatever we're getting out of this table will be understood by this object as a piano note, and it will be translated to frequency. So I want to send those values to this object. I want to actually see what it's doing for me because that's kind of interesting. Hit integer, I'm going to hook that up there. Let's do the same thing we did before. Put another integer on this side. Now let's see what we're getting out. So I'm going to type 1. So that's a little more like it. And of course, if I play around really high up here, you'll see, yes, I'm up in the 3000s on frequency. So that's taking advantage of a much wider range of human hearing. Okay. So just for kicks and giggles, let's leave this number box here and let's send that straight into triangle tilde. Okay. I'm going to make my integer thing again. And let's just listen now to what we are able to get out. So let's type 1, 2, 3, 4, 5, 6, 7. Let's go lower. All right. Cool. So as you can see, now I can actually control this triangle wave oscillator with this table. Okay. So it's kind of cumbersome to have to type numbers into a number box in order to just control this oscillator. So let's do something a little more elegant. Let's make it so that whatever is in here loops in a pattern, just like a real sequencer, and then we don't have to worry about controlling individual values, but that it will just cycle through these values, and in doing so, we'll cycle through the pitches that we hear. So there's a handy object for that, and it's called a counter. As you can see, it keeps count based on bang messages, and it's going to need a few starting arguments. The first is 0, which says count upwards, not backwards. The second is 0, which is where it needs to start the count. And the next argument is where it needs to end the count, where the loop ends. So because we have 8 steps in our table, well, going from 0 to 7, we want to also have our counter go from 0 to 7. Okay, so there's our counter, and basically what it's going to do for us is it's going to measure the number of bangs it takes in this inlet, and it's going to spit out a count out of this outlet. So let's give it something to spit its count into. How about a number box again? Let's hook the current count up to the number box, and then if you remember how to make a bang object, you can hit B. Let's hook that up to counter, and let's hit the bang and see what counter does. All right, cool. So you can actually see that it's looping around, and when it hits 7, it resets to 0 again. So we've got a counter looping in 8 steps. Okay, well this is great, because what this means is that now I don't have to type numbers straight into the table to get the corresponding Y value. I can kind of have the counter do some of that work. So I'm going to send this number into my table, and now, turn on my volume, I can control this whole little system through bangs. That's a nice one. All right. Wonderful. Okay. So next, well, what if instead of hitting these bangs, I wanted something to do that for me so that I could go in here and play around with this at will, and things would just keep rolling along at the pace I want them to. Well, I can actually control time instead with this little object called a metro. So if I make my metro, hit enter, I see what arguments it gives me. So it wants an interval, and what that means is it wants to know at what rate should it send bangs out of its outlet. And that's going to be in milliseconds. So a nice quick but not too quick tempo is going to be 200 milliseconds. So I'm going to give it 200, hit enter. And then if I scroll over the inlets and outlets, you'll see what the hints are. So it needs to be started and stopped. And if you remember from before, a really nice object to do that is a toggle. So I'm going to hit T for toggle. I'm going to hook that up to my metro. And on the other side, I just want to see what's happening. So I'm going to just make a bang, hook these together like that. And then I'm going to just start my metro and see what's going on. Okay, cool. So metro is producing a steady pulse or a steady stream of bangs at 200 milliseconds apart. I can make this faster or slower. If I said 1,000 milliseconds, then it would only light up once a second, for example. Okay, to stop my metro, I can simply unclick the toggle. Okay, so you can see how this would be useful, because instead of using this to control my counter, now I can use the metro to do that for me. And all I have to do is hit this X and set a whole process in motion, and then I'm kind of free to do whatever else I want. So I snag the outlet of this metro and put it in the inlet of the counter. Now, if I turn this on, I don't have to touch anything. It's just going, which leaves me free to open up this window and play around. You can kind of make like fun, I don't know, like pseudo video game loops this way. Cool. Okie dokie. So the last part of this demo, and one of the ways that you will show that you fiddled around with this patch, is to use additive synthesis. So again, you can think of additive synthesis as a recipe for combining simple waveforms to make something more complex. So right now you can see that I only have one triangle wave oscillator. If I wanted to use additive synthesis, I might think about adding this oscillator to another oscillator, and I mean literally adding. So let's give this a little more of an interesting timbre. Let's combine it with a sine wave. So to make a sine wave, I'm going to hit N, I'm going to do cycle tilde, and it needs a frequency. So let's make it harmonic, right? Let's give it a frequency that is a multiple of the frequency of the original triangle wave oscillator. So I'm going to give it a frequency of 900 hertz. I'm going to make it And then what I'm going to want to do is delete these patch cables because there's a few more things that need to happen. Because this is additive synthesis, I want to literally add these together. So in Max, you can actually make an add object by using addition symbols, or using math symbols, in this case addition. And since we're adding signals, it's going to need a tilde. So basically all this does is just add together what comes in each inlet. So I'm going to send my triangle wave in one inlet, my sine wave in another. And because both of these waves are basically going full blast, I'm going to want to scale this a little bit. So you can scale something by using a multiplication tilde object, and that is asterisk tilde. The hint says multiply two signals, and you can multiply two signals like these, but you can also multiply a signal by a number which must be less than 1. So it should be a decimal. It should be between 1 and 0. It shouldn't be negative at all or anything. It should be a decimal, and what that's going to do is it's just going to shrink the amplitude of the final waveform. So 0.4, 0.5 is a good bet. I'm going to use 0.4. And before I send that to my speakers, I'm going to send the signal that's coming out of here into that. Hook it up to the speakers. Sounds pretty different. So that's an example of additive synthesis. If I want to make it harmonic, what I'm going to need to do is I'm going to need to scale these incoming frequencies for this one too. So because I made my original argument 3 times 300, and I want to keep those ratios, I'm going to multiply this times 3. Now you'll notice that this times object doesn't have a tilde, and that's because it's not dealing with signals, it's only dealing with numbers. And you can also tell a difference in the patch cables. If it's numbers only, the patch cables are gray, and if there's a signal, the patch cables are stripy like this. So those are just some indicators of what kind of data you're dealing with. Are you dealing with audio signals, or are you dealing with just numbers? Okay, so I'm going to hook that up. So what this little unit here is doing is this thing is receiving whatever number it gets here and multiplying it times 3, and then it's sending that final number to cycle, which is telling this cycle which frequency it should move to. So now I'm going to get a harmonic timbre. Okay. So you can combine together waveforms like this in kind of infinite permutations. Just make sure that you're always scaling it so that you don't blow your speakers or blow your ears. I could add one more cycle just for kicks. Let's do this one times 5. So I'm going to give it an initial argument of 1500, but I'm also going to have it be times 5 whatever is coming out of immediate frequency, and going to add it and now I have a different timbre. Okay. So I highly encourage you to play along with adding together sine waves and triangle waves and sawtooth waves in different formations to get a sound that you like. And you can turn in your extra credit on Triton Ed. The assignment is posted under content. Send a screenshot of your max patch, and the way that I'll know it's yours is because it has a unique file name, and it has evidence that you fiddle around with additive synthesis stuff. The last thing I want to emphasize is that if possible, don't use headphones, don't use earbuds, use your computer speakers in case something comes out really loud. You don't want to hurt your hearing, and occasionally these things can be surprising and unpredictable, and you just don't want to blast like sine waves straight into your eardrum with earbuds. So, yeah. Okay, well, that concludes this session, and good luck.